RS-25 engines were required to reach 90% rated thrust by T3 seconds, otherwise the GPCs would initiate an RSLS abort. If all three engines indicated nominal performance by T3 seconds, they were commanded to gimbal to lift-off configuration, and the command would be issued to arm the SRBs for ignition at T0. Between T6.6 seconds and T3 seconds, while the RS-25 engines were firing but the SRBs were still bolted to the pad, the offset thrust would cause the Space Shuttle to pitch down 650 mm, 25.5 in, measured at the tip of the external tank. The 3-second delay allowed the stack to return to nearly vertical before SRB ignition. This movement was nicknamed the twang. At T0, the 8 frangible nuts holding the SRBs to the pad were detonated, the final umbilicals were disconnected, the SSMEs were commanded to 100% throttle, and the SRBs were ignited. By T plus 0.23 seconds, the SRBs built up enough thrust for liftoff to commence, and reached maximum chamber pressure by T plus 0.6 seconds. At T0, the JSC Mission Control Center assumed control of the flight from the LCC. At T plus 4 seconds, when the Space Shuttle reached an altitude of 22 meters, 73 feet, the RS-25 engines were throttled up to 104.5%. At approximately T plus 7 seconds, the Space Shuttle rolled to a heads-down orientation at an altitude of 110 meters, 350 feet, which reduced aerodynamic stress and provided an improved communication and navigation orientation. Approximately 20-30 seconds into ascent and an altitude of 2,700 meters, 9,000 feet, the RS-25 engines were throttled down to 65-72% to reduce the maximum aerodynamic forces at max Q. Additionally, the shape of the SRB propellant was designed to cause thrust to decrease at the time of max Q. The GPCs could dynamically control the throttle of the RS-25 engines based upon the performance of the SRBs. At approximately T plus 123 seconds and an altitude of 46,000 meters, 150,000 feet, pyrotechnic fasteners released the SRBs, which reached an apogee of 67,000 meters, 220,000 feet, before parachuting into the Atlantic Ocean. The Space Shuttle continued its ascent using only the RS-25 engines. On earlier missions, the Space Shuttle remained in the heads-down orientation to maintain communications with the tracking station in Bermuda, but later missions, beginning with STS-87, rolled to a heads-up orientation at T plus 6 minutes for communication with the tracking and data relay satellite constellation. The RS-25 engines were throttled at T plus 7 minutes 30 seconds to limit vehicle acceleration to 3G. At 6 seconds prior to main engine Q-TAF, MECO, which occurred at T plus 8 minutes 30 seconds, the RS-25 engines were throttled down to 67%. The GPCs controlled ET separation and dumped the remaining liquid oxygen and hydrogen to prevent outgassing while in orbit. The ET continued on a ballistic trajectory and broke up during reentry, with some small pieces landing in the Indian or Pacific Ocean. Early missions used 2 firings of the OMS to achieve orbit. The first firing raised the apogee while the second circularized the orbit. Missions after STS-38 used the RS-25 engines to achieve the optimal apogee, and used the OMS engines to circularize the orbit. The orbital altitude and inclination were mission-dependent, and the Space Shuttle's orbits varied from 220 to 620 kilometers, 120 to 335 mi. In orbit, edit. The type of mission the Space Shuttle was assigned to dictate the type of orbit that it entered. The initial design of the reusable space shuttle envisioned an increasingly cheap launch platform to deploy commercial and government satellites. Early missions routinely ferried satellites, which determined the type of orbit that the orbiter vehicle would enter. Following the Challenger disaster, many commercial payloads were moved to expendable commercial rockets, such as the Delta II. While later missions still launched commercial payloads, Space Shuttle assignments were routinely directed towards scientific payloads, such as the Hubble Space Telescope, Space Lab, and the Galileo spacecraft. Beginning with STS-71, the orbiter vehicle conducted dockings with the Mir space station. In its final decade of operation, the Space Shuttle was used for the construction of the International Space Station. Most missions involved staying in orbit several days to 2 weeks, although longer missions were possible with the extended duration orbiter pallet. The 17-day 15-hour STS-80 mission was the longest Space Shuttle mission duration. Re-entry and landing, edit. Approximately 4 hours prior to deorbit, the crew began preparing the orbiter vehicle for re-entry by closing the payload doors, radiating excess heat, and retracting the crew band antenna. The orbiter vehicle maneuvered to an upside-down, tail-first orientation and began a 2-4-minute OMS burn approximately 20 minutes before it re-entered the atmosphere. The orbiter vehicle reoriented itself to a nose-forward position with a 40 degrees angle of attack, and the Forward Reaction Control System, RCS, jets were emptied of fuel and disabled prior to re-entry. The orbiter vehicle's re-entry was defined as starting at an altitude of 120 kilometers, 400,000 feet, when it was traveling at approximately Mach 25. The orbiter vehicle's re-entry was controlled by the GPCs, which followed a preset angle of attack plan to prevent unsafe heating of the TPS. During re-entry, the orbiter's speed was regulated by altering the amount of drag produced, which was controlled by means of angle of attack, as well as bank angle. The latter could be used to control drag without changing the angle of attack. A series of role reversals were performed to control azimuth while banking. The orbiter vehicle's aft RCS jets were disabled as its ailerons, elevators, and rudder became effective in the lower atmosphere. At an altitude of 46 kilometers, 150,000 feet, the orbiter vehicle opened its speed brake on the vertical stabilizer. At 8 minutes 44 seconds prior to landing, the crew deployed the air data probes, and began lowering the angle of attack to 36 degrees. The orbiter's maximum glide ratio /lift to drag ratio varied considerably with speed, ranging from 1.3 at hypersonic speeds to 4.9 at subsonic speeds. The orbiter vehicle flew to one of the two heading alignment cones, located 48 kilometers, 30 mi, away from each end of the runway's centerline, where it made its final turns to dissipate excess energy prior to its approach and landing. Once the orbiter vehicle was traveling subsonically, the crew took over manual control of the flight. The approach and landing phase began when the orbiter vehicle was at an altitude of 3,000 m, 10,000 feet, and traveling at 150 m/s, 300 kn. The orbiter followed either a -20 degrees or -18 degrees glider slope and descended at approximately 51 m/s, 167 foot/s. The speed brake was used to keep a continuous speed, and crew initiated a pre-flare maneuver to a -1.5 degrees glider slope at an altitude of 610 m, 2,000 feet. The landing gear was deployed 10 seconds prior to touchdown, when the orbiter was at an altitude of 91 m, 300 feet, and traveling 150 m/s, 288 kn. A final flare maneuver reduced the orbiter vehicle's descent rate to 0.9 m/s, 3-foot/s, with touchdown occurring at 150 m/s, 195295 kn, depending on the weight of the orbiter vehicle. After the landing gear touched down, the crew deployed a drag chute out of the vertical stabilizer, and began wheel braking when the orbiter was traveling slower than 72 m/s, 140 kn. After the orbiter's wheels stopped, the crew deactivated the flight components and prepared to exit. Landing sites, edit. See also, list of Space Shuttle landing sites. The primary Space Shuttle landing site was the Shuttle Landing Facility at KSC, where 78 of the 133 successful landings occurred. In the event of unfavorable landing conditions, the shuttle could delay its landing or land at an alternate location. The primary alternate was Edwards AFB, which was used for 54 landings. STS-3 landed at the White Sands Space Harbor in New Mexico and required extensive post-processing after exposure to the gypsum-rich sand, some of which was found in Columbia debris after STS-107. Landings at alternate airfields required the shuttle carrier aircraft to transport the orbiter back to Cape Canaveral. In addition to the pre-planned landing airfields, there were 85 agreed-upon emergency landing sites to be used in different abort scenarios, with 58 located in other countries. The landing locations were chosen based upon political relationships, favorable weather, a runway at least 2,300 m, 7,500 feet, long, and TACAN or DME equipment. Additionally, as the orbiter vehicle only had UHF radios, international sites with only VHF radios would have been unable to communicate directly with the crew. Facilities on the east coast of the US were planned for East Coast abort landings, while several sites in Europe and Africa were planned in the event of a transoceanic abort landing. The facilities were prepared with equipment and personnel in the event of an emergency shuttle landing but were never used. Post-landing processing, edit. Main article, Orbiter Processing Facility. After the landing, ground crews approached the orbiter to conduct safety checks. Teams wearing self-contained breathing gear tested for the presence of hydrogen, hydrazine, monomethylhydrazine, nitrogen tetroxide, and ammonia to ensure the landing area was safe. Air conditioning and freon lines were connected to cool the crew and equipment and dissipate excess heat from reentry. A flight surgeon boarded the orbiter and performed medical checks of the crew before they disembarked. Once the orbiter was secured, it was towed to the OPF to be inspected, repaired, and prepared for the next mission. Space Shuttle Program, edit. Main article, Space Shuttle Program. The Space Shuttle flew from the 12th of April, 1981, until the 21st of July, 2011. Throughout the program, the Space Shuttle had 135 missions, of which 133 returned safely. Throughout its lifetime, the Space Shuttle was used to conduct scientific research, deploy commercial, military, and scientific payloads, and was involved in the construction and operation of Mir and the ISS. During its tenure, the Space Shuttle served as the only U.S. vehicle to launch astronauts, of which there was no replacement until the launch of Crew Dragon Demo 2 on the 30th of May, 2020. Budget, edit. The overall NASA budget of the Space Shuttle program has been estimated to be $221 billion in 2012 dollars. The developers of the Space Shuttle advocated for reusability as a cost-saving measure, which resulted in higher development costs for presumed lower costs per launch. During the design of the Space Shuttle, the Phase B proposals were not as cheap as the initial phaser estimates indicated, Space Shuttle Program Manager Robert Thompson acknowledged that reducing cost per pound was not the primary objective of the further design phases, as other technical requirements could not be met with the reduced costs. Development estimates made in 1972 projected a per-pound cost of payload as low as $1,109 in 2012 per pound, but the actual payload costs, not to include the costs for the research and development of the Space Shuttle, were $37,207 in 2012 per pound. Per-launch costs varied throughout the program and were dependent on the rate of flights as well as research, development, and investigation proceedings throughout the Space Shuttle program. In 1982, NASA published an estimate of $260 million in 2012 per flight, which was based on the prediction of 24 flights per year for a decade. The per-launch cost from 1995 to 2002, when the orbiters and ISS were not being constructed and there was no recovery work following a loss of crew, was $806 million. NASA published a study in 1999 that concluded that costs were $576 million in 2012, if there were 7 launches per year. In 2009, NASA determined that the cost of adding a single launch per year was $252 million in 2012, which indicated that much of the Space Shuttle program costs are for year-round personnel and operations that continued regardless of the launch rate. Accounting for the entire Space Shuttle program budget, the per-launch cost was $1.642 billion in 2012. Disasters, edit. Main articles, Space Shuttle Challenger disaster and Space Shuttle Columbia disaster. On the 28th of January, 1986, STS-51L disintegrated 73 seconds after launch, due to the failure of the right SRB, killing all 7 astronauts on board Challenger. The disaster was caused by the low-temperature impairment of an O-ring, a mission-critical seal used between segments of the SRB casing. Failure of the O-ring allowed hot combustion gases to escape from between the booster sections and burn through the adjacent ET, leading to a sequence of catastrophic events which caused the orbiter to disintegrate. Repeated warnings from design engineers voicing concerns about the lack of evidence of the O-ring's safety when the temperature was below 53 degrees Fahrenheit, 12 degrees Celsius, had been ignored by NASA managers. On the 1st of February, 2003, Columbia disintegrated during re-entry, killing all 7 of the STS-107 crew, because of damage to the carbon-carbon leading edge of the wing caused during launch. Ground control engineers had made 3 separate requests for high-resolution images taken by the Department of Defense that would have provided an understanding of the extent of the damage, while NASA's chief TPS engineer requested that astronauts on board Columbia be allowed to leave the vehicle to inspect the damage. NASA managers intervened to stop the Department of Defense's imaging of the orbiter and refused the request for the spacewalk, and thus the feasibility of scenarios for astronaut repair or rescue by Atlantis were not considered by NASA management at the time. Criticism, edit. Main article, Criticism of the Space Shuttle program. The partial reusability of the Space Shuttle was one of the primary design requirements during its initial development. The technical decisions that dictated the orbiter's return and reuse reduced the per-launch payload capabilities. The original intention was to compensate for this lower payload by lowering the per-launch costs and a high launch frequency. However, the actual costs of a Space Shuttle launch were higher than initially predicted, and the Space Shuttle did not fly the intended 24 missions per year as initially predicted by NASA. The Space Shuttle was originally intended as a launch vehicle to deploy satellites, which it was primarily used for on the missions prior to the Challenger disaster. NASA's pricing, which was below cost, was lower than expendable launch vehicles. The intention was that the high volume of Space Shuttle missions would compensate for early financial losses. The improvement of expendable launch vehicles and the transition away from commercial payloads on the Space Shuttle resulted in expendable launch vehicles becoming the primary deployment option for satellites. A key customer for the Space Shuttle was the National Reconnaissance Office, NRO, responsible for spy satellites. The existence of NRO's connection was classified through 1993, and secret considerations of NRO payload requirements led to lack of transparency in the program. The proposed Shuttle Centaur program, cancelled in the wake of the Challenger disaster, would have pushed the spacecraft beyond its operational capacity. The fatal Challenger and Columbia disasters demonstrated the safety risks of the Space Shuttle that could result in the loss of the crew. The spaceplane design of the orbiter limited the abort options, as the abort scenarios required the controlled flight of the orbiter to a runway or to allow the crew to egress individually, rather than the abort escape options on the Apollo and Soyuz space capsules. Early safety analyses advertised by NASA engineers and management predicted the chance of a catastrophic failure resulting in the death of the crew as ranging from 1 in 100 launches to as rare as 1 in 100,000. Following the loss of 2 Space Shuttle missions, the risks for the initial missions were re-evaluated, and the chance of a catastrophic loss of the vehicle and crew was found to be as high as 1 in 9. NASA management was criticized afterwards for accepting increased risk to the crew in exchange for higher mission rates. Both the Challenger and Columbia reports explained that NASA culture had failed to keep the crew safe by not objectively evaluating the potential risks of the missions. Retirement, edit. Main article, Space Shuttle Retirement. The Space Shuttle retirement was announced in January 2004. President George W. Bush announced his vision for space exploration, which called for the retirement of the Space Shuttle once it completed construction of the ISS. To ensure the ISS was properly assembled, the contributing partners determined the need for 16 remaining assembly missions in March 2006. One additional Hubble Space Telescope servicing mission was approved in October 2006. Originally, STS-134 was to be the final Space Shuttle mission. However, the Columbia disaster resulted in additional orbiters being prepared for launch on need in the event of a rescue mission. As Atlantis was prepared for the final launch on need mission, the decision was made in September 2010 that it would fly as STS-135 with a 4-person crew that could remain at the ISS in the event of an emergency. STS-135 launched on the 8th of July 2011, and landed at the KSC on the 21st of July 2011, at 5:57 a.m. EDT, 9:57 UTC. From then until the launch of Crew Dragon Demo 2 on the 30th of May 2020, the US launched its astronauts aboard Russian Soyuz spacecraft. Following each orbiter's final flight, it was processed to make it safe for display. The OMS and RCS systems used presented the primary dangers due to their toxic hypergolic propellant, and most of their components were permanently removed to prevent any dangerous outgassing. Atlantis is on display at the Kennedy Space Center Visitor Complex in Florida. Discovery is on display at the Stephen F. Udvar-Hazy Center in Virginia. Endeavour is on display at the California Science Center in Los Angeles, and Enterprise is displayed at the Intrepid Museum in New York. Components from the orbiters were transferred to the U.S. Air Force, ISS program, and Russian and Canadian governments. The engines were removed to be used on the Space Launch System, and spare RS-25 nozzles were attached for display purposes. Atlantis after its final landing, marking the end of the Space Shuttle program. See also, Edit. 1 Aircraft in Fiction Space Shuttle Orbiter. 2 List of crewed spacecraft. 3 List of Space Shuttle missions. 4 Studied Space Shuttle variations and derivatives. Similar spacecraft. 1 Buran Soviet reusable spaceplane. 2 Dream Chaser. 3 Hermes, cancelled. 4 Kuiper, cancelled. 5 Orion. Notes, edit.